Welcome to engineer's mindset. So let's say we are going to do the shear force analysis and also draw the shear force diagram for the beam as is shown. Okay, in this case we'll have a uniformly distributed load between portion B and C. Okay, so let's say how it goes now. Free body diagram. So first thing first, we have to determine what the reactions at the support. So we'll bring back the beam. Okay, at point A we have a beam support, and for beam support we have two reactions, one vertical, so this is simply RAY, and then one horizontal, RAS. So this is point A. Between point B and point C we have a UDL, and to convert the UDL to a point like I said, multiply the intensity of the UDL to the length of the UDL. The length of the UDL is 2 meters. So we have 10 times 2, which is 20 kilonewtons. Then we place it at the middle of the length of the UDL. So middle of 2 is simply 2 divided by 2. So we simply have 20 kilonewtons at the middle. This is 20 kilonewtons. So from point B to below is 1 meters. Okay, it's also 1 meters. Alright, at point D, this is the ruler. Okay. At point D, we have a ruler, and for the ruler, we just have one reaction normal to the surface. So this is point D, so we'll have a ruler, RDY, and then at point E, we have 5 kilonewtons force. So this is 5 kilonewtons force, okay? 1 meters, 1 meters, and then 1 meters apart. Alright, so that becomes the free body diagram for that beam. So after obtaining the free body diagram, next is to employ static equilibrium equation. So from static equilibrium equation, from static equilibrium law, okay, we have that summation f of x is equal to 0. Also, summation f of y is also 0. So let's start with summation f of x. Summation f of x equals 0. So that means look for the forces that point in x direction in this beam and then equate all of them to 0. The only force we'll have there is simply RAS. So this simply implies that RAS is actually what? 0. So call this that. Next is to find summation f of y equals 0. We consider vertically upward force as positive, vertically downward forces as negative. So we solve all the vertical forces and equate it to 0, considering upward forces as positive and downward forces as negative. Alright, so we start from here, point A. We have RAY pointing upwards, so it's positive. We have RAY. Also, we have the 20 kilonewtons force acting downwards, so it's negative. Minus 20 kilonewtons, okay? Next we have RDY pointing upwards, so it's positive, plus RDY, and finally we have 5 kilonewtons force pointing downwards, so it's negative, minus 5, and that's equal to 0. So we connect like terms now, RAY plus RDY, this is now minus 20 minus 5, that's equal to 0. So RAY plus RDY minus 20 minus 5 is simply minus 25, and that's equal to 0. Simply send minus 25 over to this side of the equation. Negative sign plus and equal sign becomes positive. So we simply have RAY plus RDY will be equal to 25. So call this equation 1. So I said at this point, equation 1 involves two unknowns, and that's impossible for us to solve. So what we do is simply what? Take moment about point A. Moment about the point that have numerous of forces. So we simply take moment about point A. Okay, so take moment at A. And I said summation of the entire moment at point A is simply equal to 0. So we consider clockwise moment positive, anti-clockwise negative. Okay? So that simply means now moment of these two forces at this point is completely what? 0. Since moment is force times distance, it means this force times, there is no distance between this force and point A. Two forces are already at point A. There is no distance apart between them. So their force becomes, multiply their force simply by what? 0, because the distance between them is 0. So that means the moment of these two forces at this point automatically becomes 0. So we simply take moment of every other force on the beam about point A. So taking moment of 20 kN force about point A, moment is force times distance. Total distance it takes this force to get to point A simply was from this point to this point is 1 plus 1, that's 2 meters. And again, this force is acting downward. So the moment of this force will turn about this direction to point A, which is what? Something like this. And that is what? Clockwise the direction we achieve. So we said clockwise means to be positive. So it means the moment of this force about point A is what? Positive. So we simply have 20 times total distance it takes when to get to point A is 1 point plus 1, that's 2. So 20 times 2. Okay. Also, we have RDY pointing upwards. So this force will go all the way from this direction in this direction, which is simply what? Negative to our direction. It goes all the way from this point going to this direction to point A. So which is what? Negative to our direction. So it's anti-clockwise. So the moment of this force is negative. Total distance it takes this force to get to point A is simply 1 plus 1 plus 1, that's 3, plus 1, that's 4. So it takes 4 meters to get to point A. So we simply have minus RDY times 4. Minus because it's anti-clockwise. From our direction of movement here, we say anti-clockwise which should be negative. So it's negative. And then finally we have the 5 kN force. This force is also acting downward, so it goes all the way from this place down to point A, going in this direction, which is simply what? Clockwise, so it's positive. It goes all the way from this point to point A, that is clockwise direction, so it's positive. Distance it takes its force to get to point A is simply 1 plus 1 plus 1 plus 1, 4, 5 meters. That's a entire level of beam. So we simply have plus 5 times 5. And that's equal to 0. So 2 times 5 is 20 times 2 is actually 40. Minus 4 times RDY simply gives us 4 RDY plus 5 times 5 is 25. And that's equal to 0. So we can simply collect like terms. This becomes 40 plus 25 minus 4 RDY, and that's equal to 0. So 40 plus 25 simply gives us 65 minus 4 RDY equals 0. So let's send minus 4 RDY over to this side of the equation. Negative sign crosses and equal to sign becomes positive. So I simply have 65 is equal to 4 RDY. So to make RDY substance, divide both sides of the equation by the coefficient of RDY, which is 4. So therefore we have that RDY is simply 65 divided by 4. So which implies that RDY is equal to, that is 16.25 kilonewtons. So this becomes divided for RDY. So having known this, simply substitute RDY into equation 1 into 1 to obtain the value of RAY. So from equation 1 we have that RAY plus RDY equals 25. So we know RDY. Simply we have RAY plus RDY now is 16.25, and that's equal to 25 kilonewtons. So we simply send plus 16.25 over to this side. Positive sign plus that equal to sign becomes negative. So we'll have that RAY is now equal to 25 minus 16.25. So you simply have that RAY is now equal to 8.75 kilonewtons. So this becomes the reaction at point A. Okay, so before you carry out the shear force and bending moment analysis, first thing first, obtain the reactions at point A and the force at point B. So we are going to do the shear force analysis now to see how it goes. So to do the shear force analysis, still bring back now the reactions and then put them back on the beam. And then we are going to see what we obtain. Alright, so let's bring out the beam now and see what it becomes. So we have RA already. RAY gave us 8.75 kilonewtons, so we have 8.75 kilonewtons. Okay. Next is, okay, we have point B. This is A. Remember that RAX is 0, so it's completely off. So between point B and point C, we have a UDL. So please take note, while analyzing using the UDL, you bring back the UDL. Please take it, very, very important. Now, you're not going to represent the UDL as a point load. You bring back the UDL since you're doing Shear Force and then moment analysis. So to do the Shear Force analysis, same thing applies for the moment analysis. Always bring back the UDL the way it is. So we have point C. Okay, at point D, we have RDY, and RDY was 16.25. So we have 16.25 kilonewtons. Finally, at point E, point D, we have a load of 5 kilonewtons. Okay, so that is how we do. Okay, not forgetting their distances. 1 meters, this is 2 meters, this is 1 meter, this is also 1 meters. Okay, don't forget that. Okay, now we can now start the Shear Force analysis. So Shear Force analysis. Okay, so I said that Shear Force simply means the stepwise summation of the entire force acting on the beam, from the beginning of the beam at each point of the beam to the end of the beam, considering upward forces as positive, downward forces as negative. So we have to start from the beginning of the beam. So if we start from the beginning of point A, we have Shear Force at point A. So S stands for shear, F stands for force, A simply means point A. It's simply the force that exists at point A, and that force is 8.75 kilonewtons. And it is pointing upwards, so it's positive. So I simply have 8.75 kilonewtons. So I said this same force moves from point A down to point B. Okay, so we have shear force as B. The shear force at B still remains what? 8.75 kilonewtons. So notice that at point B, there is no force at point B. So we have simply left it as what? Shear force B. If there was a force at point B, then we would have simply said shear force B prime, which means initially at point B, then finally shear force B prime. Now we will not consider the force at point B. But since there is no force at point B, this same shear force moves from point A down to point B. So the shear force at B still remains 8.75 kilonewtons. Now something happens between B and C. There is what is called a uniformly distributed load. So because of this UDL, it's now going to lead us to form what is called a shear force equation. The essence of the shear force equation is to be able to determine the point of maximum bending moment. At the point of maximum bending moment, the shear force equation is 0. So it means that we have to form what is called a shear force equation, telling us that we have passed the stage of what? Point load. This stage we are entering now is a stage that has to involve a uniformly distributed load or any other kind of load like a uniformly varying load. So that means we are now going to take what? A section. Because of this UDL, because of the presence of UDL, we are now going to take a section. So you consider a section. Let's call it x at a distance x from A along BC. So the section is actually from point A. So section somewhere along BC. Okay, this is section XX. Okay, so we section somewhere between BC, and we're simply saying let the distance from point A to the point of section simply be what? X. So let the distance from point A to this point of section be X. So if we call that distance X, then what now is the distance of the UDL from point B only to the point of the section? Because now our section was UDL. We have now sectioned the UDL. So what is now the UDL load or UDL distance? Sorry to say. Okay. So if we are saying that let distance from the section from point A to the point of section be what? X meters. So from point A to this point simply is X meters. What is now the length of the UDL? The new length of the UDL is now simply what? Since from point A to the point of section is X meters, it means if we want to do from point B to the point of section, we don't need this other 1 meters. We are actually starting from point B to the point of section. So this 1 meters is no longer needed. So simply take out this 1 meters from point X. So that means we are going to have that a new length of the UDL becomes X minus 1. So this 1 meter that we are no longer in need of, take it off from X, it becomes X minus 1. This X minus 1 is now the length from B to the point of the section. That's the length of the what? UDL. So having known this now, we now have shear force CG because we are now moving, BC. So we now have shear force BC because we are now moving what? Between the territories of point B to point C. Shear force BC now becomes, remember, the last shear force we had was 8.75. So we bring it down again, 8.75. Now we have to convert this uniform distributed load now to a point load. And I said to convert the UDL to a point load, simply multiply the UDL load by what? The length over by the UDL. So due to this section now, length over by the UDL is now X minus 1. The intensity of the UDL is simply what? Still remains 10 kilonewtons per meter. So I said the reason why it's called uniformly distributed is simply because even if we section any portion out, the load intensity still remains the same. It doesn't change. It is uniform. So it will always be 10 kilonewtons per meter regardless of the section. Okay, so we simply have minus 10 times X minus 1. So this becomes a point load. To convert the UDL to a point load, simply multiply the intensity of the UDL by the length of the length of the UDL now is simply what? X minus 1. By reason of this section, the length becomes X minus 1. Now, if we equate this equation to 0, find the value of X. This value of X is what is called the point of maximum bending moment. So whenever there is a UDL on a beam, whenever there is a uniformly varying load or uniformly distributed load on a beam, there is always a need to take that section when carrying out shear force analysis or bending moment analysis. There is always a need to carry out this section to be able to obtain this point. Because when we equate this equation to 0, we can always obtain the point of maximum bending moment. Okay? Now finally at point D, at point C, if we now consider that at C, that is X have moved from point A down to point C, X now becomes the total length from point A to point C, which is actually 1 meters plus 2 meters. So at C, X is now equal to what? 3 meters. At point C, X now becomes total distance from point A down to point C, which is simply 1 plus 2, and that's 3 meters. So at C, X is equal to 3 meters. So therefore, shear force at point C is now equal to 8.75 times 8.75 minus 10 times X is now what? 3 minus 1. Okay, so this is equal to 8.75 minus 10 into 3 minus 1 is 2. Okay, so shear force at C is now equal to, we have 8.75 minus, okay, so 10 times 2 is 20, so minus 20. So shear force at C is actually minus 11.25 kilonewtons. Okay, so this force moves from point C down to point D. Okay, this force moves from point C down to point D. So we simply have shear force D prime. So initially at point D, the force remains minus 11.25 kilonewtons. But finally at point D prime, it now encounters a force of what? 16.25 kilonewtons. So therefore, shear force D prime prime, meaning that finally at point D, this force minus 11.25 now encounters an upward force of 16.25 kilonewtons. So that is plus 16.25 kilonewtons. Okay, and this is now equal to what? 5 kilonewtons. Okay, that's now equal to 5 kilonewtons. So this force now moves shear force E prime, it now moves first to get to point E. So initially at point E, the force is 5 kilonewton. This 5 kilonewton force moves to point E first. It has 5 kilonewtons. But at point E, it now notices that there was a downward force of what? 5 kilonewtons. So we're simply going to have shear force E prime prime, which is finally at point E. It encounters a downward force. So we have 5 minus 5, and that's equal to 0. So I said at the end of every shear force analysis, you must always obtain 0 as answer. Also, at the end of every bending moment analysis, you must always obtain 0 as the answer. So we're now going to draw the diagram and see what it looks like. Okay, so to plot the diagram, we also bring back the beam. So we'll bring back our beam. So we'll have RAY. And that's equal to 8.75 kilonewtons. Also, between B and C is a UDL. So don't always forget, bring back the UDL too, the way it is. So between B and C, intensity is 10 kilonewtons per meter. At point D, we have RDY 16.25. This point D. Then finally at point E, we have 5 kilonewtons at point E. So I said all you need to do at this point is trace down all the points. So point B, trace it down. Point C, trace it down. Point B, trace down. Point E, trace down. So after that, you now examine your shear force analysis. Pick out from the highest to the lowest. So we have 8.75 kilonewtons highest. We have minus 11.25, and then we'll have 5 kilonewtons. Okay, so we have 8.75, we have 5 kilonewtons. Alright, so let's call this the origin. Let's call this the origin. So the origin is 0. Above the origin are positive values, below the origin are negative values. So we have 8.75 positive. So let's call that, keep that around there. 8.75 kilonewtons. Then we have 5 kilonewtons positive as well. So we have 5 kilonewtons. So somewhere here. So let's trace out this point. Okay. Trace out this point. Okay. Next we have minus 11.25 negative. So let's call that here 11.25. Okay, so there's no need to put negative since it's below 0, so it's already negative. Minus 11.25. So let's trace it out as well. Down. Okay. So shear force at point A is 8.75 kilonewtons. This is 8.75 kilonewtons. This is line A. So simply what? Asterisk. Okay. Shear force at B still remains 8.75 kilonewtons. This is line B. This is 8.75 kilonewtons. So we also want asterisk. Alright. Now between B and C, okay, shear force at C gave us minus 11.25 kilonewtons. So this is shear force at C. This is line C. This is minus 11.25. So you asterisk. You have that. And finally, shear force at D. Okay, shear force at D is 5 kilonewtons force. Okay, shear force at D is 5 kilonewtons force. This is 5 kilonewtons force. This is line D. So you asterisk. Okay, finally, shear force at E is 0. Shear force at E is actually 0. This is line E. This is 0 mark. So you asterisk. So you have that. So it starts from the origin. The shear force diagram for the point node is simply what? A straight line. So this is a point node. So starting from the origin, connect to what? Point. Okay, the first shear force is 8.75. Now this 8.75 force moves from point A down towards point B. So we'll have shear force at point B. Now between B and C is a UDL. The shear force diagram for a UDL is a slant line. Is a slant line. Okay. So we connect from point B to point C. We connect with a slant line. That's what shows shear force diagram for a UDL. So we connect the slant line. Okay, this same force moves from point C down to point B. Okay, that's at D prime. Yes, it moves from point C down to point D, and then finally at point D, it encounters now an upward force of what? Which is this 5 kilonewtons. So we'll have an upward force. Okay, this same force moves from point D down to point E before it now encounters the downward force, which actually brought it towards 0. So we simply have this. So this is the shear force diagram. Simply shape. Simply shape. Simply shape. That's how the shear force diagram. That's what the shear force diagram for that beam looks like. Alright guys, I will see you in the next video with more questions on shear force analysis. In the next video, we'll start analysis on the bending moment. Please stay connected, subscribe to the channel, invite your friends for more subscribers, and of course, go through the playlist on shear force and bending moment to get a full package of shear force and bending moment analysis. I will see you in the next videos. Thanks and cheers.